All right, what's up, guys? I'm gonna just work out the solutions for this checkpoint so we don't have to go over them, next time we meet, and we can just kind of do, whatever we decide is best. So let's get to it here. Um, I'll just tell you, I'm gonna, pretty strictly stick with his notation. So, uh, whenever I write a big M in the work I'm about to do, you'll see that will be the mass of the Earth, and whenever I write a big R, that's going to be the radius of the Earth. So in each of these problems, essentially, there's a mass that is at some point, some height, above the surface of the Earth, and I'll just call that height h. Okay, so hopefully that's all right. Let's get into it. So for retrieval here, I mean, this one is, I don't know, it is a little trickier than maybe it would seem, in my opinion at least. But the idea is that this force of thrust is doing positive work on the rocket, right? Which means, in a sense, that it's putting energy into the system. Though you could, if you want to really convince yourself of this, you could do something like this, right? So let's consider the limiting case in which the thrust force, let's call it T, is equal in magnitude to the gravitational force. So what I'm saying is this, right? I'm saying the force of thrust is going to be G big M little m over little r squared, right? And so this varies with little r, and you have to be aware here, right, that this little r is the distance from the center of the Earth to the center of mass of the rocket. And so initially, yes, this would just be a big R, but it varies, right, because it's moving upward, and its distance from the center of the Earth is increasing, right? So we have this. In this case, right, let's say in this case, the net acceleration, or we'll just say the acceleration, right, of the rocket is 0, because you have the gravitational force pulling down on it, right, and the force of thrust propelling it upward. So we can just think about energy, right? So the initial energy is going to be something like this. We'll just say it's E naught is 1/2 m v naught squared. Sorry, minus, right? Because now we're doing this sort of more exact formula for the gravitational potential energy. So that's going to be G big M little m, and the initial value here is just going to be big R, right? Because it starts at the surface of the Earth. And then its energy at some later time will be what I'm about to write here. Okay, and again, right, I'm writing that the kinetic energy is the same because we're kind of considering the limiting case in which the force of thrust has the same magnitude as the gravitational force, right? Which means that this thing doesn't speed up or slow down, for that matter, right? So the kinetic energy is the same. So this energy difference, let's say the corresponding energy difference is delta E, right? This is just, not delta E. This is E minus E initial. And I'm just going to copy and paste this. It's this minus this, right? And we'll say that what this works out to be is G big M little m over big R minus G big M little m over R plus H. Okay, and then we'll clean this up a little bit. We'll write g big M little m times 1 over big R minus 1 over big R plus h. So this is basically our answer, okay, here. And we need to think about, like, is this quantity positive or negative, right? So, you know, this is a good skill to have. And I mean, we could do two things here. One, we could just argue that this this R here, right, is smaller than this R plus H term, regardless of what H is, as long as it's positive, right, which it should be. And so what we have here is like 1 over some large number minus 1 over some larger number, right? Which means that this number here will always be positive and smaller than this number here, right? But if you can't see that, it's obviously okay. And this is like one of the situations where, you know, calculators aren't, I guess, the worst thing in the world. Yes, I said it. I said that sometimes they're useful, but we could just plug in some numbers, right? We could say, well, like, what if R is 1.64 times 10 to the 6? I mean, which it is in my notation, right? And then we say, well, let's think about H being, I don't know, like 1,000 kilometers or something like that, right? So what we have down here is we have 6.4 times 10 to the 6th, right? Plus, and we said 1,000 kilometers, so that's 1,000 times 10 to the 3rd meters, right? And this is a positive number. It's a very small number, right? But it is positive. So, you know, maybe this is a direct way you could convince yourself kind of that the work should be positive, or maybe you could just see it, right? I think a lot of you probably could just see it, but I personally would like to go through and do like a little quick calculation to kind of convince myself that what I'm doing makes sense, right? Okay. Hopefully that's all right. Now, this comprehension one, right? This one, I would have gotten this wrong, all right, if I had gone into this quiz with no preparation. I mean, admittedly, I'm kind of bad at this orbital mechanics stuff, just because I haven't thought about it or worked with it in a long time. But you know, like, I don't know that I can give you a satisfactory answer here. But I found something that kind of makes sense to me, and what you can think about is, I'll just bring up the Stack Exchange thing that I'm referencing here. I'll put the link to this in the video, or yeah, in the video description, because I think this is a very good discussion that they're having here. Someone says, I've read several Stack Exchange posts on this, blah, blah, blah. Let's see. I cannot motivate why providing an impulse tangent to an orbit will cause the planet's satellite to go into a circular orbit of greater radius. The Hohmann transfer, I guess, is what this is called. Whereas a radial impulse will cause it to go into an elliptic orbit. So this guy is actually not completely correct, I guess, with what he's asserting in his question. But that's okay. I mean, people, you know, I think people are downvoting him. At least maybe one person did. Sorry, you ever go to the Stack Exchange, right? I've been saying this all along. You have some of the smartest people, and they're just so mean, all right? But, you know, it's okay. We're STEM majors. We have no ego, right? Anyway, this is a good sketch of what happens here, right? So what this guy's saying is that this satellite, let's say, is initially in a circular orbit, right? And at some point in its orbit, an impulse is applied, right? And that's what we have here in the question is essentially some kind of force is acting on this thing to speed it up. Because the speed in a circular orbit is constant, right? And that's maybe the key to really understanding what's happening here. So what you have then is you have basically an increase in speed. And let me just quote what he says, because I don't think I could say it better than he did. He says, the idea of the Hoffman transfer is to increase or decrease the satellite's speed instantaneously at any one of these 2 points to match the speed required for a circular orbit of that radius. So when the satellite is at its furthest from the focus, the apogee, a boost in speed, can put it into a circular orbit with the maximum radius of the elliptical orbit, while at the closest point, a reduction in speed can put it into a circular orbit with minimum radius of the ellipse. Maybe this is actually not what I... let me actually think about this for a second here. So maybe the reason I'm getting confused is because this Hoffman transfer thing is like, you have to apply two separate impulses, right? So what this looks like for like space geeks, right, is like maybe you have something in a circular orbit, you apply an impulse to it, its orbit then becomes elliptical, right? Then you apply another impulse to it, and then the orbit goes back to circular, but now with a larger radius than the original orbit. Okay, so let me maybe put it this way. In a circular orbit, the speed, right, the tangential speed is constant, okay? In an elliptical orbit, it's not, right? So there is one unique speed, right, that gives a circular orbit, and you could solve for this using, you know, Newton's second law for the centripetal case, right? There's one unique speed that gives us a circular orbit, and if you increase that speed, then you cannot have a circular orbit, right? Because this thing is gonna do something, and then it's gonna come back to where it started, and it's gonna have a larger kinetic energy, a larger speed there, right? And so maybe what I should have focused on is this, where he says, for a circular orbit, the magnitude of velocity is constant, and its direction is always perpendicular to the radius. For an elliptical orbit, the magnitude of velocity varies, and its direction is perpendicular to the radius at only 2 points in the orbit, right, at the ends of the ellipse's major axis. And this is actually what I should have read. At the further of these 2 points from the attracting focus, the apogee, the speed is too slow for a circular orbit at that radius. At the closer point, the perigee, the speed is too fast. Okay, so the speed is too fast for it to be a circular orbit, and it becomes an elliptical orbit. Okay. But I would encourage you to read this discussion, because, you know, there's some good things being said here, not just in this response, but the other ones too, and probably will make more sense after you look at that than after just listening to me explain. So I'll just say, you know, see stack exchange discussion, and I'll put the link in the video description. If I ever forget to do that, one of you please remind me. Okay. So analysis. Here we're talking about geosynchronous orbits, right? So this means that the orbit has a period of exactly 1 day, right? So the first thing we probably need to do is note that there are, we'll call it big T equals 86,400 seconds in 1 day. Okay. So the tangential speed of the satellite is then going to be, we'll just call it V, and this is going to be a circumference over a time, right? So that's what I'm saying here with big C, is a circumference, because we know that a speed is a length or a distance over a time, right? So the natural generalization for that distance in the case of circular motion is the circumference of that circle. So we're going to say this then. We're going to say that this is 2 pi r plus h, right? That's the circumference of the circle that, you know, has a point on it that's a distance h above the Earth's surface. And then t is just t, right? This is the period. So you have that, and then what we do, right, is we apply Newton's second law for the case of circular motion. And what this looks like, right, is we'll just say the net force in the centripetal direction is going to be the gravitational force. I'll just scroll up a little. G big M little m over r plus h quantity squared, right? And this is going to be equal to mv squared over r plus h, right? We're just kind of thinking back to, I don't know what, like week 3 or 4, whenever we first started talking about centripetal motion. And this allows us to write, right, we can cancel a factor of little m on both sides. We can cancel a factor of r plus h in the denominators. This allows us to write that v squared is g big M, like writing m, big M over r plus h. Right, let me just make sure I didn't make an algebra mistake here. Cancel the m's, cancel a factor of r plus h. Yeah, it looks good to me. I mean, you know, I'll never guarantee you I won't make algebra mistakes. But, you know, the process here is good. I can say that much. Okay, so we now know what v squared is, and we've written out what v is, so we can just take this thing and square it, right? So, demanding, right, that v squared equals v squared, we have, and I'll just copy and paste this thing. I'll fix it up. So we'll say that the 2 pi becomes 4 pi squared, right? This r plus h thing is now squared, and t is now squared, right? And from Newton's second law, this equals this. Right, that. And so we want to solve for yeah, we want to solve for h here, which is a little bit gross, but you know, I mean, we can do it. I mean, Mathematica can do it, right? I don't know, some of you, when I talked to you, expressed a little bit of unease about solving for something cubed, which is what we're going to wind up with here. So maybe I'll just actually keep going with the algebra. So this is what we'll do. We'll take it very slowly, and this is for my sake and yours. We still have 4 pi squared, but we're going to multiply both sides by r plus h. So now we wind up with a cube, right? I have t squared downstairs there, and now this is just gm. Is this good? I think it's good. Yeah. And then we have to get this r plus h thing by itself, right? So we have now r plus h cubed is going to be g big M t squared over 4 pi squared. And then the next thing we need to do is we need to raise both sides of this equation to the power of 1/3. Okay, so what we then do is we say, well, actually, I'll just say r plus h, because if we raise the left-hand side to the power of 1/3, we just get r plus h. This then equals g big M t squared over 4 pi squared, all to the power of 1/3. Right, 1/3. Therefore, h equals this junk minus r, right? And I don't like this stacked fraction in the exponent here, so let me just change that. I literally think I'm the only person who cares about this, but I cannot control myself. Okay, there we go. And then let's do one more thing that nobody cares about. Let's just make sure everything's aligned up nicely. There you go. Isn't that beautiful? Yeah. So you should find something like this, right? You know, up to a power of my ability to do algebra correctly, but go through, check it yourself, make sure that you can do it. And yeah, it's some number, right? Some whatever. I mean, as a sanity check, at least we see that it's larger than r. Or wait, no, this doesn't mean it's larger than r. I'm gonna stop. I think it's fine. Okay, so then this last one is let's see here. The work needed to put a 1,000 kilogram satellite into a circular orbit at a height of 400 kilometers above Earth's surface, starting from rest on the ground. Okay, so this is another thing where we can just, you know, compare energies. We can compare the initial mechanical energy to the final mechanical energy, and then note that whatever difference we observe between the two has to be accounted for by the work done on the satellite. So let's say the initial mechanical energy of the satellite is purely gravitational potential energy. Okay, so we'll just call it E initial, and this is negative big G big M little m over big R, and that's it, right? This is because the prompt says starting from rest on the ground, right? So no kinetic energy. Okay, now the final energy, right? And here's where I think maybe a lot of you, you know, made a mistake, and I made this mistake too when I actually first tried to solve this. Like, honestly, I probably would have gotten like 2 wrong on this quiz, just real talk. But you know, that's okay. I did my time. Right. Not that that helps you guys, but yeah. Anyway, the final energy here is going to be some kinetic energy, right? So 1/2 mv squared minus plus the new gravitational potential energy, right? Because the potential energy itself is negative. So that's going to be this term that I've written here, right? We're now saying it's h 400 kilometers above the Earth's surface, right? And I don't think I said this, but you always have to remember, right, with gravitational potential energy and the gravitational force, you need to consider the center of mass distance. You know, well, let me say it like this: the distance from one object's center of mass to the other object's center of mass, right? So that's why we always have to, you know, say that something at the surface of the Earth has non-zero gravitational potential energy, okay? Because its distance from the Earth's center of mass is just the radius of the Earth, right? But you all probably know that, but I should say it. Okay. Anyway, we need to do something here, though, right? So I'm sure he mentioned this in lecture. Maybe some of you saw this result and were like, "Oh, cool, okay." But it actually is pretty useful, right? So maybe he showed it to you, but didn't necessarily stress its utility. So let's talk about this again. Let's look at Newton's second law, right? From Newton's second law, we can write this, and we're thinking about the centripetal forces on the satellite here. We're going to write that the gravitational force for this particular case equals mv squared over r plus h, right? This is just the condition for the uniform circular motion. And notice that this mv squared term is basically our kinetic energy, right? It's double our kinetic energy, right? Because 1/2 mv squared is the kinetic energy. Double that is mv squared, is what we see in the numerator here, right? So let's keep going with that. I mean, we could try to be fancy and multiply both sides by 1/2 and all that, but let's not do that. Let's just solve this for mv squared, right? So what I'll say is that this clearly says that mv squared equals g big M little m times r plus h over r plus h squared, right? So we can cancel a factor of r plus h. So let's just do that. This goes away, and then now down here we just have r plus h. Okay, so then 1/2 mv squared equals 1/2 times this part, right? So our kinetic energy can be written in all the same terms as the gravitational potential, right? And this is kind of important. And so let's just write this as this term that I'm putting in now, right, which is the gravitational potential energy. No, sorry, that's the kinetic energy expressed like a gravitational potential energy, right? Because it looks kind of like a gravitational potential energy. Minus this thing, right? And what you have here essentially is you have, you know, this is basically 1/2 x minus x, right? Which is negative 1/2 x. X here would be the g big M little m all over r plus h, right? So what we can say is that this is going to be negative 1/2 g big M little m over r plus h. So this is our final energy, right? Our final energy. And in this situation then, right, we, like I said, I almost forgot what we were doing, but we can say that the work is what accounts for the difference in energy. So we'll say something like work equals delta E, which is just going to be E minus E naught, right? Which is just going to be this. It's going to be the final energy minus the initial energy. Let me get that equal sign out of there. That shouldn't be here. Okay, so we'll clean this up a little bit because I'm not going to get a number here, right? I'll leave that to you guys, but you know, I want to set you up at least to you know, be able to see something, which I'll talk about in a second. But what we have then, right, is we have that this is 1 over big R minus 1 over big R plus H, and right, we want to focus on this part of our result because it should be positive, right? That's sort of what our intuition says, is that the work should be positive. It's kind of got to be, right, to basically give this thing the energy required to be in a circular orbit, right? From just the energy required to just, you know, chill there at sea level on the Earth, okay? So you should go through and maybe calculate the number here. It's not such a terrible thing to do, I guess. But, you know, we can probably just see without even doing that we get a positive result here, okay? Now, again, I'm not sure that I didn't make any algebra mistakes along the way here, but, you know, feel free to ask questions if anything's unclear. And, you know, while I'll say that my math isn't always 100% correct, the reasoning is good, okay? So, you know, hopefully this does help. And, you know, just let me know if you need anything, as always, all right? I'll see you guys later.